We mentioned the scope of a quantifier on Friday. I want to think about what happens when one quantifier is in the scope of another. So I think about something like a universal quantifier. A universal quantifier says for all x, this thing is true. Well, maybe the thing that is true also contains a quantifier. So for all x, p of x, if this has its own quantifier, then the quantifier inside p of x is nested in the quantifier for all x. An example. I'm pretty sure you've heard this rule before. If I'm in the universe of discourse being numbers, the order in which you add numbers doesn't matter. X plus y is the same as y plus x, but that should apply to all numbers. So it applies for all x, for all y. But I can think of there being an extra set of parentheses here. And then I see this statement is a quantified statement. For every value of y, x plus y is the same as y plus x. So it doesn't matter which side y is on. But that's also true for all x. So this quantifier is in the scope of this one. There's a name for this rule in algebra class. What do we call it? Unfortunately, no, it is not the associative property. The associative property is the next one I'm going to do because it involves three variables. What is this one? Addition is, there's an adjective there. It's not associative, it's commutative. A lot of our algebraic rules are universally quantified statements. We just don't tend to think of them that way. Now, Colin, you mentioned the associative rule. The associative rule is about order of parentheses. The order in which I associate two numbers being added, the order in which I associate three numbers being added, doesn't matter. So I might write something like this. And I see I've nested this time three quantifiers. The statement, x plus y first added together, then added to z, is equal to x plus first add y and z. So this is equivalent to this. The association from the parentheses doesn't matter. But it's three quantifiers because I can say, well, this applies to all the z's. It also applies to all the y's. Notice how the z is inside there. And it applies to all the x's as well. The quantifiers don't have to be the same. Let's turn this from a symbolic statement to an English one. What does this say in words? Again, I'm in the universe of numbers. Gesundheit. Colin? For all x, there exists a y, so that x plus y is 0, is a literal translation. But I think the English needs to be massaged a little to actually say what I want to mean here. Evan? Okay. For all x values, there's at least one y value, absolutely. Because this quantifier doesn't say anything about unique, right? But I said there were a couple of different ways we could read that upside down A. The universal quantifier can be read for all x. It can also be read for each x, right? Because that's a giant and statement. It's true for this x, it's true for this x, it's true for this x. Each x has a y that when you add, you get 0. Pick a number. Seriously, pick a number. Got it in your head? Put a minus sign in front of it. What happens when you add those two things? You get 0, don't you? Aha. What this says is that every number has something that I can add to it that will give me 0. But it's not the same y for all of the x's. It's for each y. A generalized statement is that the order of my quantifiers matters. This really forces my choice of y to be made after I choose x. If I reversed those two quantifiers, that doesn't say the same thing. Because we read our quantifiers in order from outside to inside, from left to right in this case. So this says there's some y. For any x that you add to it, you're going to get 0. That means there's one number out there that no matter what you add, you get 0. Can you think of any number that you could add whatever you wanted to it and get 0? It doesn't make sense. So the order is important. Here, y is chosen first. Then our x value. And that doesn't work. There isn't one number that no matter what I pick, when I add, I get 0. Up here, the fact that the order is chosen x first, then y, means that I can change the value of y for each individual x. I can't do that in this version. Even if I wanted to reverse the quantifiers, I might not be able to make the same statement be true, especially when they are different. However, when they are the same, let's go back and write this statement. Does the order of the quantifiers matter there? Aha. Here I'm saying for all x, for all y, no matter which x you pick, and no matter which y you pick. You will often sometimes see this abbreviated exactly as that, as an and statement. So we'll really make one quantifier because that's really an and. But most of the time, we want to be careful about the order in which we select things. Existential quantifiers far more often require order to be carefully monitored because our choices cascade in order. There exists an x, there exists a y. Well, now that y depends on my choice of x. If I reverse them, then I would say, oh, you choose y first, and then your choice of x matters. So they could be related to each other somehow. You may or may not see this same collapsing when dealing with existential, as opposed to when dealing with universals. So when I write this set of quantifiers, then I'm saying there is one particular y that is going to work for all the x's. I choose the y first, and then it's got to work for all the x's. But if I write it in the other order, then my y can be chosen differently for each individual x. And it only has to work with that one x each time. That's the for every part column that should apply to all of them, but it applies to each one of them in a distinct fashion. Sometimes, in some textbooks and in some arguments, you'll actually see them write this second version. They'll write y depends on x. So they might write y depending on x, like it was a function. Your choice of x influences your choice of y. Yes? That's not always written down, but I think it can be helpful depending on the situation we find ourselves in. Questions? Yes. Oh, of this particular for the x plus y equals 0? Yes, that's that this particular rule is an additive identity. Sorry, an additive inverse, because we find the thing that is the inverse of our number, we get back 0. But we'll talk more about what rules go with what in a later course. Additive inverse. Linear algebra, we'll talk about where specific rules get used. Abstract algebra, we'll talk about where specific rules get used. There are a lot of different places where, hey, I need to know the rules that go under this particular setting. This has to do with vectors. So you might see it in Calc 3 if you're in that. You might see it in linear because vector spaces are things we build in linear algebra. And so there's a lot of places where these ideas, commutative associative identities and inverses, come into play. It has to do with these structures underlying the math we are doing. Trying not to go way off on a tangent because that's really, really cool and is where this course begins and we end way down there in several more courses. Better? Okay. I want you to translate to English for me. Now, you can translate this literally from symbols to English words. We're still in the universe of numbers. But then let's see if we can write it in a nicer English sentence. What is the literal translation of this? What do you got, Colin? For all x values, for all y values. If x is positive and y is positive, then x times y is positive. I am sure I have seen this written without ever using the word if or then or the phrase for all. I want you to think about the following sentence. Do you see an if then in that sentence? Do you see a quantifier anywhere in that sentence? Oh, crap. But what this sentence says is that the product of two positive numbers. So if you give me, notice what I just said, if you give me two numbers and they are each positive, if you give me two numbers and they are each positive, then their product will be positive. We say sentences in math all the time that sound just like this. The derivative of a continuous function may not be continuous. We've written things like that in lots of other classes. Those of you who haven't done calculus and continuity and derivatives yet, don't panic, we'll get there. But the sentence itself doesn't sound like an if-then. It doesn't sound like it's quantified. That sentence applies to any two positive numbers. And there's my quantifier. It's implied in the English and explicit symbolic. That's one of the best parts about symbolic logic is we get rid of any sort of vagary and make things more precise. And much more of a pain in the ass to write down, but more precise. Questions? They don't have to be about numbers. People. The following is weird. This is a very, very sad social situation, since I'm dealing with people and friendship. What the hell does this sentence say? Chew on this one for a minute. Starting all the way on the left, there exists an X. There is a person. All Y for all Z. If, what's my if part here? Colin?
If X and Y are friends, and if X and Z are friends, and if Y and Z are not.
So, X has two different people, Y and Z, that they are friends with. This tells me they're different. This tells me friends with the first person, friends with the second person. If X is friends with Y, friends with Z, and they're different people, then hang on. What's that symbol? Aha, Y and Z are not friends. There is somebody that has a bunch of friends that are only friends with him, they don't like each other. This is a person whose social circle looks like no connection to anybody else. None of these people are friends with each other. They're all friends with X, but they don't like each other. If you pick any two of them, that would be this part. Different people, they're not friends. There is someone whose friends are not friends with each other. Makes hanging out in a group really weird. Questions? Let's go the other way. Here's a sentence in English. Turn it into logical symbols. In the universe we were just in. How would I quantify this? So if I write this, there exists y, then what? So there are my quantifiers. What's the proposition itself? I'm going to use that proposition. You've given me the people, right? And I want them to be friends. Make sense? My problem is that I don't like the way these quantifiers are ordered. Ignoring this sentence, let's translate that. We choose y first. There is a person. No matter who you pick for x, for every x, they're friends with that person. This actually says y is friends with everyone. Is that what that sentence says? Okay. If we reverse the order of these quantifiers, and I write this, no matter who you pick for all x, right? Pick anyone. There is someone who is their friend. No matter who you pick, there's someone who is their friend. And this time I did use at least one, since that existential thing doesn't say anything about having one and only one friend, right? The reason for the order matters here. I'm not unhappy with the sentence, there exists a person who is friends with everyone. I like that idea. I'm sure that's not me, but I'm sure it's someone somewhere. I should be a little more careful here, because it is possible that the person who is your friend is you. Maybe you're your only friend. I don't think of many of you as that misanthropic and hating all other people, but how could I say in here, how could I addend this to make sure it's someone that isn't you? So now I've changed the sentence just a little. I'm not discounting the idea that you can be your friend, but I'd like you to have another friend. Somebody other than your imaginary friend, I guess. The elephant from Inside Out, Bing Bong, something like that. Okay. How do I add this piece in? Aha! So I make sure that it's somebody else. Perfect. What if I wanted to be that unique person? I only have one friend. Now I need to be a little more careful because this is going to be a bigger nest. There are more things involved here. I mean, I start with this part, right? Except now I want to work the quantifiers differently because I'm saying someone, not for all. I'm saying someone. So this time, there exists a person that has a friend. That's not themselves, right? I didn't put a uniqueness in there. I could say that this, I could use the exclamation point here, right? If I said this, then there's only one Y that fits the bill. Yeah, yes, but I'm not sure I like that. Let's see if we can do it without the exclamation point. So how do I say and that's the only one? Huh. Well, that would just tell me that Y and Z weren't friends. I don't want X to be friends with that other person, right? I do want another quantifier though, because I want to say for all the other people other than Y, X isn't friends. So now I'm going to add another quantifier inside the scope of this for all Z, where Z is not Y and Z is not X and X is not friends with Z. So that's the way to get rid of needing that little exclamation point and say, oh yeah, and for the rest of them, it doesn't work. I am leaving in the possibility that X could be friends with themselves. So you see how that exclamation point really replaces a lot of extra stuff? It replaces another nested universal quantifier. Questions? I have spent an awful lot of time doing calculus. This is the formal definition of a limit. It's really a nested quantifier statement. For every epsilon you pick, there is some delta so that when you're close enough to A, close enough being defined as within delta, then your Y value is close enough to L. So we use nested quantifier statements foundationally in mathematics. They are the basis of what we are doing. I tend to think of nested quantifiers as loops. Here's a holdover from my programming days. If I see a statement like this, I get a value for epsilon, and then I start looking for values of delta until I find one that works. If I have a universally quantified statement, and I say something like this, right? Then I pick an x, until one works. And literally in my head, I have this image of a grid. The coordinate axes, right? X is on one axis and Y is on another. And I just say, okay, you picked an X. Now I'm going to look at all the Y's until I'm done. And if I reverse this, then you've chosen that Y first. Oh, wait a minute. See, I forgot to write something down here. Pick X and loop through all the Y's until one works for every X. So I have to do that over and over and over again, right? If the first X, the second X, the third X, I only need one Y for each one, but I could get a different Y for each one. Here, fix an X. Then check all Y's to make sure our statement is true. But again, I think of that as a loop. Okay, here's my X value. Is it true for this Y, this Y, this Y, this Y? And I go all the way through all the Y list. Given the predilection I had for sci-fi movies, I used to picture a little light moving down a row of Y choices for each X that got lit up. And I could see this little blinking light thing in the back of my laboratory going, beep, 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 beep. Bad 50 science movies. Questions? What about a double universal? What's that looping going to look like? So I would do this, but I'd have to do this for each of the X's, right? So I'd start with the first X and make sure I could fill in all the Y's. Move to the second X, make sure I can fill in all the Y's. Third X, make sure I can fill in all the Y's. I have to do it for all the X's. In finite piles of things, this is a giant AND statement. But in infinite piles of things, like real numbers, this is going to be a lot harder to check. Similarly, for an existential, if I had this, then I'd look for I'd say, okay, here's the first X. Do any of the Y's work? Here's the second X. Do any of the Y's work? And the first time I find a light that lights up, stop. There is an X, there is a Y, it works. I just need one example. questions. Very end of class on Friday, I said that we were going to look at negations. And when we negated a universal, we got an existential. When we negated an existential, we got a universal. But now I've got more than one quantifier. So how do I negate a statement? It is not true that for all x, for all y, oh, that should be an existential. Stop, scratch, rewrite. For all x, there exists y, xy equals 1. It is not true that for all x, there is some number you can multiply x by that gives you 1. What's the number that breaks? What choice of x is going to make that false? If I pick 1, 1 times 1 is 1. 0. There's nothing I can multiply 0 by that's going to give me 1. 0 times everything is again 0. So I know the statement is false. Let's put the negation in front of it. How do I write this? Well, if I think of that extra set of parentheses I was talking about, I move the negation from out there to in here. And when I move the negation across a universal, I get an existential. So I moved the negation from the left of the quantifier to the right of the quantifier. No, yes. But now I have a negation outside a quantifier. Let's move it in again. So what is this logically equivalent to? When I move a negation across an existential, it becomes a universal. And I negate the proposition that comes after it. Now, I don't like writing not xy equals 1. I like the fact that in math I have a symbol that says the same thing, but you could leave that negation on the xy equals 1 setup, but this is equivalent. There is at least one value of x, so that no matter what you multiply by, you never get 1. The number in question is 0. No matter what you multiply 0 by, you never get anything but 0. You're definitely not getting 1. The important idea here is that I don't want to flip multiple quantifiers in my head, especially if they might be nested in different places. All of these were nested one after the other at the beginning. If I go back to this sentence, I could flip from here to here and from here to here fairly easily, but moving that negation across this quantifier and across all those and statements is going to take a little work. And that's why I always move the negation a single bump at a time. Questions? The purpose of writing all these logical, formal statements is not just to be a pain in your ass. That happens to be a fringe benefit, but it's not the purpose of doing all of this. The purpose of doing all of this is to make a logical argument. As crazy as it sounds, math is not foundationally about calculating. I know every course you've ever taken in math up to this point in time has been, here's a formula, let's figure out how to use it. Here's a process, let's calculate something. Take a derivative, do an integral, all sorts of things we do. But this is set up to clarify the language so that instead of asking how, I can ask why. To do that means I need another type of argumentation idea. In English class, we're taught how to write paragraphs and how to put out supporting evidence and how to justify the things we are saying. I need to do that mathematically. My goal is to develop both quantified and unquantified methods of deduction and inference. And the rules that govern those ideas require me to be precise. And that's why I switch stuff to this kind of formal statement. In a very deep fashion, this is what every piece of computer code does. It interprets the sentences you write into formal logical ands and ors that your little computer chips can then light up as ones and zeros. That's what a compiler does. It interprets programming statements into machine code. This is the sort of code that formally mathematics works in. I need to know what it's doing with these codes. And that's what we'll talk about Wednesday. I would then say to you, hey, we've just finished section 1.5. That means the homework will be due on Friday. Who's got the schedule? You should look. You know what Friday is? We don't have class. On Friday, there is a middle school math competition in Sicilian Hall. It will be running from about 9 to 1. That's going to be in the middle of this course. I am participating in helping run this. If you want to come cheer on the middle school math students as they try and qualify for state and national competitions, finals should start around noon. I will see you all on Wednesday, and then we'll talk about rules of inference. Have a wonderful rest of your day.